of aircraft on the ground. Aircraft must not deviate laterally, that means sideways, more than 15 degrees from the runway center line. Confines of the runway as specified in the aerodrome manual, 30 feet from the runway center line. So minimum controllable speed. So this is the minimum controllable speed. Let's read this document. Minimum controllable speed is defined as the minimum calibrated airspeed. So remember, it's calibrated airspeed. All speeds that are slow in value, that are small in values, are calibrated airspeeds. Speeds that are fast in values, that are big in values, are equivalent airspeeds. Okay. So VMCG is defined as the minimum calibrated airspeed during takeoff run at which if the critical engine fails, it is possible to maintain directional control only using only aerodynamic controls. Okay, so it is possible to maintain directional control left right using only aerodynamic controls. VMCG must not be greater than V1. Very important. VMCG is a design certification speed which is established by the manufacturer. So another very important MCQ point, it's established by the manufacturer, not the captain, not your company, not the DGCA during certification process. It's the minimum speed at which when critical engine is suddenly made inoperative, it's possible to maintain control of the plane using the rudder control alone. Okay, so just the rudder control without the use of nose wheel steering, as limited by 150 pounds of force, and the lateral control to the extent of keeping the wings level to enable takeoff to be safely continued using normal piloting skill. Assuming that the part of the plane accelerating with all engines operating is along the center line of the runway, under standard VMCG criteria, its path from the point at which the critical engine is made inoperative to the point at which recovery to a direction parallel to the center line is completed may not deviate more than 30 feet laterally from the center point or center line at any point. Manufacturers may be able to nominate a deviation value other than 30 feet provided that the value is published within the flight and performance manuals for that aircraft. Deviation values of less than 30 feet can be particularly useful when considering operations from narrow runways. The conditions under which the certification tests are conducted include: a bare and dry runway is considered calm winds, nose wheel steering disconnected to simulate a slippery runway. VMCG must be calculated or established with the airplane in each takeoff configuration or at the option of the manufacturer in the most critical takeoff configuration. The critical engine must be subject to a sudden failure. In addition, the following criteria must be met: maximum available takeoff power or thrust on the operating engines, most unfavorable center of gravity, aeroplane trim for takeoff the most unfavorable weight in the range of takeoff weights. Okay, so this is some theory that I just read out. So remember, the correct answer is 30 feet from the runway center line. Next, VOR position 61° north, 25° east. Variation at VOR 13 east. Estimated position of aircraft 59 north and 25 east. That means both VOR and aircraft are located on the same longitude. Variation at aircraft 20 east. What is the radial on which aircraft is situated? Let's say this is your north datum. Okay, so VOR is at 61° north, aircraft is at 59° north. That means VOR station is to the north of aircraft. So let's draw that VOR station. This is your aircraft, let's say. So now, aircraft is directly to the south of VOR station. That means aircraft will be located on radial. 180 from the VOR. Radial 180 from the VOR. Now all VOR radials are magnetic in direction. So we must convert this 180 bearing, which is true bearing from the VOR, into magnetic one. Now there are two types of variation available: variation at the VOR, variation at aircraft. Now in solving VOR questions, you will use the variation existing at the VOR location. In solving questions involving NDB, ADF, you are going to use variation at aircraft position. So here variation at VOR is 13 degree east. So variation 13 east. So magnetic will be least. So magnetic direction will be 180 minus 13, which is 167. Yeah. So that means aircraft is actually located on radial 167 in terms of magnetic direction, 180 in terms of true direction. Okay. So next. Okay, so pay attention to the hemisphere you are in and the values. Next. The phase difference between the reference and variable signals on QDM 050 with a variation of 10 degree west for a conventional VOR is what? Now the principle of operation of VOR is based on phase difference. Phase difference between the reference signal and the variable signal. Let's say this is your reference signal. This is your reference signal, and this is your variable signal. Variable signal. Now the phase difference, the angular difference between this reference signal and variable signal is 090 degree. That means that means this particular bearing will be called radial 090. This particular bearing will be called radial 090. Reference signal is going to remain fixed with respect to the magnetic north datum. Okay, and this variable signal will continuously rotate around the VOR station. Now the moment, the place where you measure the phase difference between them will be equal to the bearing from that UR station. Now here the phase difference is 090. That means this becomes bearing 090 from the VOR station. So any bearing from the VOR station is nothing but radial. So we call this radial 090. Now any aircraft which falls anywhere in this line of bearing 090 will be set to be or position to be on radial 090. Now in this question, QDM is 050. What is QDM? QDM is magnetic bearing to the station. QDR is magnetic bearing from the station. This is nothing but radial. Okay. Now we are told to find the phase difference. That means we have to find the radial. Okay. In other words, we have to find QDR or we have to find radial. If QDM is 050, QDR will be directly reciprocal of that, opposite of that. So QDR will be 180 plus 50, that is 230. Now you need not apply variation here because QDM and QDR are already magnetic in direction. If they had given QUJ, QTE, which are true bearings, then we would have applied this variation to convert that true bearings into corresponding magnetic bearings. So QDR is 230. So the phase difference between the variable and reference signals on QDM 050 is equal to 230. Meaning, let's say this is your VOR station. Reference signal is, so this is the reference signal of this particular VOR station. Okay, and variable signal is 230. Variable signal is 230. That means phase difference is 230. That means The angle between this reference and variable signal is 230 degrees. Okay, next. QDM and QD are measured in degrees, which take into account Earth's true north, Earth magnetic field, aircraft compass north. Now, like I said, QDM is magnetic bearing from the VOR station. QDR is magnetic bearing from the VOR station. QDM is magnetic bearing to the VOR station. So, magnetic, that means they include Earth magnetic field. Okay, 35. To obtain a QDM, it is necessary to add the true bearing to the station to aircraft heading. So QDM formula is QDM, that is magnetic bearing to the station, is relative bearing plus magnetic heading. Okay, relative bearing plus magnetic heading. So you let's say this is your north magnetic north datum. This is where the VOR station is located. Okay, in the easterly direction. Your aircraft is here, is on a heading of is on a heading of 050. Okay, so heading of 050 will be measured with respect to true this magnetic north 050. Then what is the relative bearing between your aircraft and this VOR station? Relative means bearing means the angular difference relative to your aircraft. So you will start measuring that angle beginning from your aircraft heading to that VOR station. So that angular difference is equal to 40 degree. 50 minus 90 is 40 degree. That means your aircraft and VOR station are separated by 40 degree. Now if you want to go to this VOR station, okay, instead of flying a heading of 050, you want to go to this VOR station, what bearing will you fly? What bearing will you fly? The bearing to be flown will be equal to this heading of aircraft plus this additional relative bearing. Okay, so heading plus relative bearing. So 050 plus 40, that is 090. So your aircraft will start flying 090 towards that VOR station. Now I have drawn this aircraft here, but the correct way is to draw the aircraft at the center point here. So in that case this addition will be valid. Okay, so QDM equals to magnetic bearing to the station equals to your magnetic heading plus relative bearing. Now relative bearing cannot be magnetic or true, it's just the angular difference. So the relative bearing of the station plus magnetic heading. Option Bravo. Question 36. Density altitude is what? Pressure altitude corrected for variation from non-standard temperature. True altitude corrected for outside air temperature. Indicated altitude corrected for non-standard temperature. So it is pressure altitude corrected for variations from standard temperature. Density altitude equals to pressure altitude plus 120 into ISA deviation. Let's say I am at mean sea level. The ISA conditions state that at mean sea level you must have a temperature of 15 degrees Celsius, 15. Let's say the current ambient temperature at mean sea level is warmer than that, it's 30 degrees Celsius. So that means there is a deviation between what ISA says and what the reality is, right? So deviation is equal to 15 degrees Celsius. Its actual ambient temperature is warmer than ISA temperature by 15 Celsius, right? So you are going to put that value in place of ISA deviation. Pressure altitude will be mean sea level, so 0 plus 120 into 15. So 120 into 15 will be what? So when you multiply, it will be equal to 1800. So density altitude equals to 1800 feet. So what have you observed here? Your pressure altitude, that means you are at mean sea level, 0 feet. But density altitude is approximately 2000 feet. That means your aircraft is positioned at mean sea level, but the performance that it will generate, the performance that it will give, it will produce, will be equivalent to performance produced at 2000 feet. Now we all know that as you go to higher and higher altitudes, atmospheric pressure goes on decreasing. With decreasing atmospheric pressure, the density of air, that is the thickness of air, also decreases. Now as the air becomes thinner and thinner, that will be a drawback for your aircraft engines. Your aircraft engine will not be able to generate as much thrust as it would with density of air that is thicker or greater. Okay, so more the density of air, more the generation of engine power. Less the density of air, less the generation of engine power. Okay, so density altitude is that's why calculated at the time of takeoff to make sure to ensure that you have favorable conditions for takeoff run, for climb, and also for landing, so that you may have adequate landing distance available and favorable conditions for missed approach or climb after missed approach or go around. Okay. So density altitude is very important and its pressure altitude corrected for variations from non-standard temperature. When temperatures are colder than ISA, okay, colder than ISA, so that works very good for your aircraft. Okay, that works in favor of your aircraft. Your aircraft performance will increase more than your expectations, beyond your expectations. But when temperatures are warmer than expected, the performance of your aircraft gets sterilized. So next, traffic load or payload consists of what? The total mass of passengers, baggage, cargo, including any non-revenue load and fuel. So this is wrong. Your traffic load or payload will not include any fuel component. Total mass of passengers, baggage, cargo, non-revenue load, yes. DOM plus useful load, including fuel on board. So that is wrong. DOM plus useful load is a takeoff mass. So you always begin with basic empty mass. The basic empty mass plus variable load will give you dry operating mass. What is variable load? Variable load includes your crew baggage, food, beverages, any other materials like that. When then after that, DOM plus fuel on board or takeoff fuel will be equal to operating mass. DOM plus payload will be equal to your zero fuel mass. After that, operating mass plus payload will be equal to your takeoff mass. Zero fuel mass plus fuel on board will be also equal to your takeoff mass. DOM plus useful load also equals takeoff mass. What is useful load? It is fuel on board plus payload. Okay. Next, takeoff mass minus trip fuel will be equal to your landing mass. Will be equal to your landing mass. Next, when aircraft has turned 270 degrees with a constant attitude, okay, and bank, that means the attitude of your aircraft is maintained throughout the turn, the attitude with respect to the horizon. Bank angle is also maintained. You are not changing your bank angle amidst the turn. The pilot observes the following on a classic artificial horizon. So you will have to remember this table. When you make a 90-degree turn, the artificial horizon will underread the bank angle. So let's say you're turning your aircraft at a bank angle of 20 degrees. The bank angle indicated by your attitude indicator will be less than 20 degrees, 15, 16, something like that. Underreading will happen and it will show a false climb indication. If you're making a level turn, okay, a level turn. So in spite of that, the artificial horizon will indicate a climbing attitude. Turning through 180-degree bank angle will be indicated correctly, but pitch error again it will persist. It will indicate a climbing error, a climbing pitch, attitude, next turning through 270 degree, overreading of bank angle, and pitch error, it will show a false line indication. A complete 360-degree turn, correct bank angle, correct pitch attitude. Okay, so you are making a 270-degree turn. So what will you observe? You will observe pitch up attitude. So that is A is wrong. This is right, and overreading of bank angle.